Okay, back at it. So if you haven't seen the last video, we were talking about why the heck one might care about eigenvectors and eigenvalues, okay? So, and just to sort of brief you on that in case you haven't seen it, go watch it though, okay? You should go watch it. But in any case, we talked about applications in data analysis, so a method called principal component analysis, and sort of understanding, wow, so eigenvectors can help us extract sort of the points of most variance and be able to sort of reduce the dimension of a data set and simplify things for us. We also talked about its application in physics. So because, as we talked about in the previous video, eigenvectors are almost these points of stability when you apply a transformation to them. All that happens to them is that they get stretched or compressed in some way, okay? But they stay the same, they have the same direction still. If you're thinking about like 3 dimensions and Euclidean vector spaces. But in any case, it helps us understand stability in a system in that case. Like if you're looking at rotating objects, you can find, axes where it naturally rotates, these axes of rotation, okay? That's why we care about eigenvectors and eigenvalues. So without further ado, let's get into the math. So how do we calculate them? All right, I'm sure that's on the minds of all my viewers. Well, it's actually not too bad. So let's look at the equation TV equals lambda V. We can do an example if you want. We looked at an example in the previous one, so perhaps not. But one way to look at it in general is, well, let's bring it to the other side, okay? So what do we have then? We have TV minus lambda V equals 0. Okay, that's interesting. It would be nice to bring that V out, so let's do that. So we have in parentheses that T minus lambda. Okay, so we can't subtract. We can't exactly, it's kind of sacrilegious to subtract a linear map and a scalar. So we're just going to multiply our little lambda here by our identity transform, okay? This is okay. This doesn't change anything because the identity multiplied by our lambda here is still just lambda, okay? So that's okay. This is what we have. Bring out the V, we have 0. Okay, but this here, this is a linear map, is it not? I mean, I didn't prove this, okay? Granted, but if you subtract 2 linear maps, do you not still get a linear map? It's worth checking, so I encourage you guys to try this. I'll leave it as an exercise to the viewer, per se. But again, if you perform any sort of arithmetic operations on a linear map, you still preserve that linear property, right? All we're doing is subtracting them, multiplying this by scalar. We still have linearity here. So we're applying a linear map to V and we're getting 0. What does that remind you of? Well, we talked about range and null space. Which one is it? Okay. Well, the linear map is getting mapped to 0, so it's null space, okay? So this means that V is an eigenvector if and only if V is in then the null space, the null of T minus lambda I. Okay. Well, this kind of gives us a condition for when T actually has an eigenvector, because we're yapping all about these eigenvectors and eigenvalues, but how do we know that T actually has one of these? Well, sometimes the null space is trivial. When is that? Well, the null space, what I mean by trivial again, is that it just includes 0. And V then, we made the condition V can't be equal to 0. So then, if the null space was trivial, we wouldn't have any eigenvectors by this logic, okay? So when is that? Like I said, well, we talked about this, all right? We had a whole video on this. The null space is trivial if and only if T is injective. If and only if this thing here, I should say, this thing that we're taking the null space of is injective, okay? Boom, okay. Now we have a condition, so this is technically a proposition. So V is an eigenvector of T if and only if T minus lambda I is injective. is not injective, because if it is injective, then our null space is trivial and we don't get any nice vectors in that null space. If it is not injective, then there's got to be, by that equivalence, there's got to be some kind of non-zero vector in the null space. Okay, so this is true. Well, we can expand this a little bit, because remember, we also made a little nice video about the equivalence of injectivity, surjectivity, and invertibility when we're dealing with operators. Actually, it was specifically when we were dealing with same dimensional spaces. So when dimension of V was equal to the dimension of W, and we're looking at a map from V to W. Okay, but obviously, if we're going from V to itself, dimension of V is trivially equal to dimension of V. So that's actually a subcase of that. And so this is equivalent then to say, so I'm just going to say if and only if 2, T minus lambda I is not surjective. Okay, sorry, I should have clarified after this, right? So that result specifically said that it was equivalent that a linear map under this circumstance, so in this case, we're dealing with operators, so that holds, that a linear map is surjective if and only if it is injective, if and only if it is invertible, okay? And so we have that one more thing, minus lambda I, supposed to be T, is not invertible. Great. Okay. So that is how we deal with sort of not necessarily computing these eigenvectors, so I kind of lied initially, but sort of having a condition for when we can find these eigenvectors and eigenvalues, okay? So I think next, it's worth looking at an example of a map that actually doesn't have an eigenvector, okay? Because, again, when it comes to things in math, you want to always find counterexamples of things. If everything was sort of unicorns and rainbows, you know what I mean? Everything would be homogeneous, everything would be the same, everything would follow from everything. But, you know, there's a lot of different functions, and a lot of these functions don't have the same properties as others. So let's look at an example of something that even intuitively wouldn't have any eigenvectors. So let's look at this, okay? You guys might recognize this if you've done any physics, okay? This map here, okay? So what do we have here? Well, we're taking a vector, xy, and we're mapping it. So again, T is a linear operator from R2 to R2. Okay. What we're doing is we're swapping the coordinates here and we're taking the negative. Okay. So visually what we're really doing, okay, let's take some xy here. All right. Well, we're swapping the coordinates. Okay. So I don't know, if this is your x, this is your y. Then what we're doing is we're instead, if you think about it, swapping the coordinates is almost like taking an inverse, okay? So we're doing this. And then, not only that, but we're moving our y to the negative side. So then we're moving our x value to the negative. Okay, so then we have this. Now notice how these points, if you draw that line towards the origin and match them up, it's almost like we've rotated this point 90 degrees over to this side. And actually, if you look at the rotation matrix, this is the reason I was saying, if you've done any physics, this might look familiar. If you apply xy to the rotation matrix, okay, I forgot what the rotation matrix was. There's a formula for it. It's pretty intuitive. But your two-dimensional rotation matrix, and you plug in theta equals pi over 2, 90 degrees, then you get exactly this function, this minus y x. And that's because what I just explained here, well, all this is doing is it's taking a vector xy and then moving it counterclockwise 90 degrees. Okay. Well, if we're rotating every single non-zero vector, right, then how the heck are we going to be able to have any eigenvector? Because as we explained, eigenvectors get expanded and contracted. They have to keep the same direction here. But that's not possible. And so we can prove that in the real numbers, indeed, this is going to be a little problematic. Okay. Well, let's see. So let's just do the math. I mean, this is just basic algebra. It's a system of equations, TV equals lambda v. Let's do it. So t xy equals lambda xy. All right, well, what does that give us? That gives us, what's TV? Or TV is negative y. X is equal to, let's distribute that lambda throughout. Okay, so now we have a system of equations. We have minus y equals lambda x, and we have x equals lambda y. All right, but we have a little value for x here, so let's substitute it in that first equation. So we have minus y is equal to lambda squared, right? Because it's that lambda times lambda y. Okay. Well, if I want to get rid of that y on both sides, I want to divide by it. But what if it's 0? Well, if y was 0, let's backtrack here. X is equal to lambda y, so then x would be 0 too. But that's problematic because we need v to be non-zero. So we can't have y equals 0. So we can comfortably cancel it out. So we have negative 1 equals lambda squared. Oh crap. What does that look like to you? Lambda has to be imaginary, right? It's plus or minus I. Well, what did we say? T is a linear operator from r squared to r squared. We're only dealing with the real numbers here. So there's going to be no real eigenvectors or eigenvalues. But there will be complex ones, no? Right? Because if we allow complex ones, then we can just take that square root comfortably and we get plus or minus I, okay? And then we can go in and calculate the corresponding v's. So we would have lambda is equal to plus or minus I, and then we'd plug those back in and get formulas for possible values of x and y. Okay, so that begs the question, if we simply extend our perception to complex numbers, can we always find at least one eigenvector or eigenvalue? Now that, my friends, I must leave you with a cliffhanger, okay? And so in the next episode, which will hopefully be posted tomorrow, we will answer that question. We will continue this quest down this beautiful topic of eigenvectors and eigenvalues. So until then, peace out.